Okay, Physics 30s. Let me show you old Roemer's understanding of how that light is, or the speed of light. So if you can see in this animation, old Roemer was observing the moon Io around Jupiter. The blue dot that's circling there is Earth, and the sun obviously is disproportionate, so this isn't to scale. But so Roemer, when he was looking at Jupiter, he would literally see this. So you could see Io, then it would disappear. So he'd start the clock, and then Io would come out from Jupiter and then come in front of Jupiter. He could keep watching it, but every 42 and a half hours, there would be an eclipse of Io. So he had to, obviously make lots of observations in order to see the consistency of this, but it was very consistent, and he started making this observation. Now, what was interesting, though, is he observed it when the Earth was close to Jupiter, and then as you can see, the blue, it moves away as the Earth goes throughout its orbit. He gets farther and farther away from Jupiter, and the eclipse starts happening late. In fact, it got so late, like 6 months from observing, it was 22 minutes later than it was when he observed it 6 months prior to that. So he started scratching his head and going, wait a minute, there's got to be an explanation in terms of the speed of light, because he's observing reflected light, of course, from the moon Io. So as you can see, his conclusion is that light took 22 minutes to cross Earth's orbit. And even back then, they had a pretty good gauge of what the Earth's orbit was. And so he basically made his speed of light calculation by taking the diameter of Earth's orbit and dividing it by that 22 minutes. So we have distance divided by time, and bang. So yeah, he got, like it says here, 220,000 kilometers per second, when the actual speed is, about 300,000 kilometers per second, or 3 times 10 to the 8th meters per second. So that's all Roemer's contribution, which I wanted you to just visually see that because it's kind of hard to describe it. So, but here I want you to see this as well. This is an animation of Albert Michelson's apparatus. And maybe I can kind of half zoom in there a little bit. So you can see, in this case, we have an 8-sided mirror that's spinning, and this animation shows a flat mirror. It's supposed to be a parabolic or curved mirror, but that's okay. You can get the idea. If we were actually to shoot light out of a source, it would hit one of the faces of the mirror, and then while the light travels to the parabolic mirror and back, the octagonal mirror is spinning. So in this one, see, the mirror is spinning too slowly. It's not spinning fast enough for the light to when it comes back, to hit the mirror just right. And that's something I didn't emphasize before. We're applying the principle of reflection here. The angle that the light hits the mirror is the angle that it leaves the mirror, okay, with reference to what we call a normal. So the angle of incidence is equal to the angle of reflection. So here's an animation of it happening too fast. Okay, so let me kind of get up in here. So see, it's just this is where you'd be spinning the mirror too fast, and it's not directing the light into the observer's eye, or where it can be detected. So the perfect setup then, of course, would be this. So this is where the light is. He's got it spinning just right, so that when the light spins and it comes back and hits a mirror surface, it will go into the observer. And this is what Michelson was, and you just had to fine tune it until it was nicely lined up. So here's another view of that, which I kind of like. So you look at it from a different perspective. The light would be coming out, hitting the rotating mirror to the parabolic mirror and back. So obviously light, we're trying to figure out that light is a wave. This is sort of an animation showing that light's a particle, which is just fine. But I like those because they this may help you a bit to help you understand Albert Michelson's 8-sided mirror. So you definitely need to be prepared to answer speed of light questions using a Michelson mirror apparatus, which this is animating. So I hope that's helpful.